Today's topic is Mazur's chapter 4, Momentum. So this time I think you should skim Mazur's chapter 4 and really focus on the concepts half. Don't worry so much about the equations. And see if you can do some of the checkpoints. I'd eventually like to make this video lecture self-contained so you don't have to read the book. But I like Mazur's chapter 4 so much that I don't really think I could discuss it nearly as effectively at this point unless you've at least skimmed through it to see the ideas. I'll try, but I think you're going to get more out of the lecture if you read, at least skim the concepts part of the chapter first. The slides I show in today's video are linked from the Canvas assignment and from the comments at the bottom of the video. So Phys 8 slides 04.pdf. Momentum is the product of mass m and velocity v. Velocity is a vector. Mass is a scalar. When you multiply a scalar by a vector, you get another vector. So the product of mass and velocity is a vector which we label p, the vector momentum. Okay, so momentum is mass times velocity. Momentum is a vector. Velocity is a vector. We, for the first 9 chapters of the book, are dealing only with the x-axis. So we will worry only about the x component of momentum. So we'll say that p sub x, that's the momentum in the x direction, equals the mass times v sub x. This is the velocity in the x direction. So the x component of momentum equals the mass times the x component of velocity. By the way, Chapter 4 will use the word inertia to refer to m. It's a little bit confusing, especially since m makes you think mass. The reason why Chapter 4 so scrupulously uses the word inertia instead of the word mass when writing the symbol m is that mass plays 2 roles in physics. One role that mass plays is how much an object is attracted by gravity. Okay, so the strength with which Earth attracts you gravitationally is proportional to your mass. It's also proportional to Earth's mass. The other function that mass plays in physics is that the more massive an object is, the more difficult it is to accelerate, the more difficult it is to change its velocity. So the second property of mass, that the more massive an object is, the more difficult it is to accelerate it, the more difficult it is to change its velocity, that property of mass is called inertia. So when referring to the fact that it's more difficult to make more stuff change its velocity than it is to make less stuff change its velocity, Mazur uses the word inertia, even though it's the same letter m. I will say mass because I've learned over the years that it's more natural for you if I just say mass. But in the context of momentum, you want to bear in mind that the role that mass plays is that role of inertia. So inertia is the same thing as mass. Inertia is mass. But in particular, when we refer to inertia and when we refer to mass in the context of momentum, we're referring to the fact that it is more difficult to accelerate an object which is more massive. You have to push harder on something which is more massive to get the same change in velocity. Okay. The reason we're talking about momentum is that momentum is a conserved quantity. This is a hugely important idea in physics, the idea of a conserved quantity. A conserved quantity can be transferred from one object to another, but it can never be created or destroyed. A conserved quantity is something that can never be created or destroyed. It can be transferred from one thing to another, but it can't appear out of nowhere or disappear into nowhere. So maybe a more familiar idea from everyday life is sort of the idea of money collected among several bank accounts. So maybe you have a savings account and a checking account, and let's assume there's no monthly interest and there's no monthly fee. So unless you somehow externally put money in or externally take money out, you know that the total quantity of money should stay constant. And maybe you shuffle things back and forth between your checking account and your savings account, but still the total stays the same. So a conserved quantity allows us to use this really useful bookkeeping device that says, well, as long as I can draw a line around somehow this system, actually system is another really important concept that's going to be useful when using conserved quantities. So, you have your two bank accounts, and you can say, well, let's say the system consisting of my checking account plus my savings account there might be flow back and forth between savings and checking of money, but let's say there's no money going in or no money going out unless I explicitly make a transaction of that sort. So then if I define this system, then I can say that the total money in this system is conserved. Okay, so momentum is a conserved quantity. And if you're able to define a system such that you know that no momentum enters or exits that system externally, then you can say that the total momentum of that system is constant. And in particular, if we isolate a system so that that system is not pushing on or pulling on anything outside of the system, then the momentum of that system as a whole is constant. So if objects within a given system, maybe they push on each other or pull on each other, but they do not push or pull on anything outside of the system, then that's called an isolated system, and the momentum of an isolated system is constant. So that's going to be extremely useful because it then allows us to do momentum bookkeeping. So let's just look really quickly at an example of momentum being transferred from one object to another. And then let's just look really quickly at an example of two objects interacting with one another in such a way that you can see that the total momentum afterward is the same as the total momentum beforehand. So you can see that one of the two objects will gain momentum going this way, one of the two objects will gain momentum going this way because they push on each other, but the total momentum of the two objects is the same before and after their interaction with each other. So momentum is mass times velocity. Why is that factor of m there? It's because imagine throwing a baseball and then imagine throwing a heavy medicine ball. And you know that you will tend to recoil much more from throwing a heavy medicine ball than from throwing a baseball. It's much more, somehow it takes you much more effort. You have to push much harder to change the velocity of a heavy medicine ball than you do to change the velocity of a relatively lightweight baseball. Now, when you think about that, it's somewhat complicated by the fact that not only are you pushing on the medicine ball, but also the ground is pushing on you. So it's not only are you, when you throw the medicine ball, you're interacting with the medicine ball, but you're also interacting with the ground. The contact of your rubber shoes with the ground will prevent you from recoiling. And you can see in a video clip in just a second, Mary and me throwing a medicine ball back and forth, first when we're both wearing rubber-soled shoes, so each of us has good contact with the floor of the auditorium, and so then it's not easy to identify any isolated system, so then you don't see the expected recoil. Then we will see what happens when Mary puts on roller skates. So then, when Mary throws the ball, from the instant before she throws the ball until the instant after she throws the ball, the system consisting of Mary plus the ball is isolated because Mary is only pushing on the ball. She's not, and only the ball is pushing on Mary. So there's no interaction with the ground to worry about. So then you'll see when Mary throws the ball toward me, she recoils. Then a short time later, you'll see that when Mary catches the ball after I throw it back to her, she recoils again. And then she'll throw the ball back to me, and you'll see her recoil again. So whether Mary catches or throws the ball, you will see her recoil because there's no interaction with the ground to stop her from recoiling. So each one of these throwing or catching events demonstrates this idea that the momentum of the ball plus Mary system before the throw, just before the throw or just before the catch, is the same as the momentum of the ball plus Mary system just after the throw or just after the catch. Just imagine what it feels like to throw a heavy medicine ball. Now imagine doing the same thing while standing on a sheet of ice. Okay, ow, okay. Another word you'll see in chapter 4 is impulse. The definition that Eric Mazur uses for impulse is a transfer of momentum from outside of a system to inside the system, or from inside the system to outside the system. So a transfer of momentum across a system boundary is what Eric calls impulse. So impulse is sort of like a bank transaction from outside or inside your bank account. It's something that can change your bank balance. So if you do draw a nice boundary around a system, if you can eliminate all possible exchanges of momentum between that system and the outside of that system, you say that momentum is constant for the system. If you can't say that, then you attribute the change in the system's momentum to some impulse. So the impulse is a transfer of momentum into or out of a system due to interactions with something outside of the system. If you watch me throwing and catching the ball in that clip, you see that if you take the ball plus me system, its momentum is not constant. You notice that the ball is moving toward me, I catch it, and then after I catch it, nothing is moving. So somehow, just before I catch the ball, there is net momentum toward me, and just after I catch the ball, there's zero net momentum of me and the ball together. And that's because there is some external influence of the ground which is preventing me from recoiling. So that transfer of momentum from the ground to the ball plus me system is an impulse. So we'll use impulse as a bookkeeping mechanism to account for the possibility that momentum enters the system or leaves the system from outside. But most commonly, we will consider the case where there is no impulse, there is no interaction with anything outside of the system. We'll consider an isolated system. We'll consider a system whose parts interact only with each other. So if there are two objects, and usually our system will just have two objects in it, we'll have two objects in a system, and they only push on each other, or they only pull on each other, and that means that the total momentum of the system before they interact is the same as the total momentum of the system after they interact, and that lets us do bookkeeping. So imagine a scenario where initially we have object 1 moving to the right and object 2 standing still. And here's the little clock at midnight. And then later, here's the little clock at 4 p.m., let's say. And later we have object 1 standing still and object 2 moving to the right. And let's say object 1 and object 2 interact only with each other, so they form an isolated system. So they might push on each other, but nothing outside that 1 plus 2 system is pushing on anything inside that 1 plus 2 system. So then we can say that the total momentum, so here's our initial state and here's our final state, we can say that the total momentum of the initial state is the total momentum, of the final state. And how do we write that more carefully? Well, first of all, let's just use x components. And let's also say that the momentum is the momentum of cart 1 plus the momentum of cart 2. So then we will say P1x initial plus P2x initial equals P1x final plus P2x final. And we know that momentum is mass times velocity. So then we can go one more step, and we can say that m1 times v1x initial plus m2 times v2x initial is m1 times v1x final plus m2 plus m2 times v2x final. And this looks like a little bit of a mess. It's much easier to talk about changes in velocity of one cart and the other cart. As a matter of fact, there are a couple things we can say here. One is that P1x final minus P1x initial equals the opposite of P2x final minus P2x initial. So that's the same thing as saying delta P1x equals minus delta P2x. That's saying if object 1 gains momentum, then object 2 must lose the exact same momentum. If object 1 loses momentum, object 2 must gain that same amount of momentum, so that the change in one momentum is the opposite of the change of the other momentum. In other words, the sum of the two momenta has to be unchanged. What's the implication for changes in velocity? Well, we'll see that we have m1 times v1x final minus v1x initial is the opposite of m2 times v2x final minus v2x initial. And another way to write that is that m1 times delta v1x is opposite of m2 times delta v2x. And we can summarize that in a way that's easier when you're watching things collide on a track by saying that the change in v1x divided by the change in v2x is minus m2 over m1. So if you see two carts of different masses collide on a track, then the more massive one will have a smaller change in velocity. The less massive one will have a larger change in velocity. And each change in velocity will be inversely proportional to the corresponding mass. And if the change in object 1's velocity is to the left, then the change in object 2's velocity will be to the right. So we're going to see this in some examples of two carts colliding on a track right now. So we're going to see large numbers of examples of problems where we have two things heading toward each other, or one is heading toward the other, which is stationary, and you know what's happening beforehand, and you want somehow to predict what's going to happen afterwards. And we're almost always going somehow to reason that the system must be isolated. I mean, there might be some cases where you can argue why it's not, but you sort of argue why is it that you can understand that the two objects are interacting only with each other and not with anything else. So that lets you then draw some nice system boundary around the two objects, and then you say the system is isolated. And if you're solving a problem with equations, we will almost always write down m1 v1x initial plus m2 v2x initial equals m1 v1x final plus m2 v2x final. Again, we like to imbue equations with meaning. We don't just like to write down equations. What does this mean? Momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. What does that really mean? Total momentum of the system before they collide equals the total momentum of the system after they collide. Okay, so you add up So kind of like money in the bank, momentum is a quantity where you combine two things, you can add up what's inside them both. So you add up the total momentum of the two constituents of the system before, and you say, well, that must be the same as the total momentum of the two constituents of the system after, as long as you're able to argue that the system is isolated so that you know no momentum flows in or out of the system, which you can then argue on the basis of nothing outside the system is pushing on or pulling on anything inside the system. Now, when we watch things on video colliding on the track, there's a much more intuitive way to look at this that aids the eye, which is that you're going to see two things collide with one another. You see, when these two things collide, object number one is going to experience a delta V1, let's say the x component, in that direction. Well, it's not yet. And then object 2 is going to experience some kind of delta V2 in that direction. And it's not the delta V's that are going to be equal and opposite, but it's going to be the delta P's that are equal and opposite. If they're the same mass, then their delta V's will be equal and opposite. But if they're, in general, they'll be different masses. So it's really their changes in momentum that will be equal and opposite. And so you want to know how big, so if you have the x-axis pointing this way, then probably object 1 will experience a change in velocity whose x component is negative. Object 2 will experience a change in velocity whose x component is positive. And you want to compare those two things. You say, well, how does delta V1 compare with delta V2? The minus sign tells you that if object 1 experiences a change in velocity to the left, then object 2 must experience a change in velocity to the right, or vice versa. And this ratio tells you that the more massive object will experience a smaller magnitude change in velocity, and the less massive object will experience a larger magnitude change in velocity. So let's look at that again. Okay, let's watch some examples of a blue cart and a red cart colliding on a little horizontal track. And each cart has little wheels whose purpose is to make the rolling of each cart relatively frictionless. So then we're going to envision that the two carts are interacting only with each other and not with anything else from the instant before the collision until the instant after the collision. And in the first case, the two carts will be the same mass. So the blue cart will have the same mass as the red cart. And the first example, the blue cart is moving to the right initially, and the red cart is stationary. So since we're having the x-axis point to the right, then V1x initial is positive, and V2x initial is 0. 0 velocity means stationary. Positive velocity means moving to the right. After the collision, we'll see, in this particular case, that V1x final is 0, V2x final is bigger than 0. In other words, what you'll see is that cart 1 after the collision is stationary, and cart 2 after the collision is traveling to the right. What does that imply for each change in velocity? So delta V1x is V1x final minus V1x initial. So 0 minus positive is negative, so delta V1x is negative. What does that mean? It means its change points to the left, and that will make sense because it starts out going to the right and then it stops. So what is the change in its velocity? That is a left-pointing change in velocity. Meanwhile, the red cart will start out stationary and end up going to the right. So that is a positive change in velocity, the x component, because positive minus 0 is positive. So delta V2x will be positive. So we'll have delta V1x is negative, delta V2x is positive. So they'll be opposite each other, because the ratio of the two masses is the same. So if V1 experiences a positive change in velocity, then V2 experiences a negative change in velocity of the same magnitude as long as the masses are the same. Let's watch that. The next scenario we're going to watch on the little track is the same two carts, equal masses, but The blue cart will be moving to the right, the red cart will be moving to the left, and then they're going to collide, and after they collide, you will see the blue cart moving to the left and the red cart moving to the right. So initially, blue is moving to the right, red is moving to the left, and then when they're all done and they finish colliding afterwards, I guess like in the final state where Missouri's book would show like a clock at 4 p.m., then you're going to see the blue cart going to the left, the red cart going to the right. So what does that mean? So this is final minus initial. Final is negative, initial is positive, the x-coordinate. Here, final is positive, initial is negative, the x-coordinate. So negative minus positive, negative minus positive is a negative change, and positive minus negative is a positive change. So delta Vx of the blue cart points to the left, delta Vx of the red cart points to the right. Because their masses are the same, those two changes in velocity have the same magnitude. So if the blue cart recoils to the left with 1 unit of change in velocity, then the red cart recoils to the right with 1 unit of change in velocity. Let's watch that. Okay, now let's change the assumption that the two masses are the same. The way we're going to do that is we'll stick a little brick into cart 1 such that we effectively double the mass of cart 1. So now the mass of cart 1 is 2 times the mass of cart 2. Okay, so cart 1 has 2 units of mass, cart 2 still has 1 unit of mass. And let's start out in the initial state with cart 1, the blue cart, moving to the right, and cart 2, the red cart, stationary, minding its own business. And what we're going to see is that after this collision, we have cart 1 moving to the right with a smaller, okay, so here's initial with the little clock kind of close to midnight. Here's final with the little clock kind of like at 4 p.m. So after the collision, we will see the blue cart, cart 1, moving to the right still, but with a smaller velocity. So it's goes from moving to the right a lot to moving to the right a little. And then we'll see the red cart goes shooting off to the right with a pretty big velocity. And so remember, delta V1x over delta V2x is minus m2 over m1. So that would be minus 1/2, right? So that's minus 1/2 if m1 equals 2m2. If m1 equals 2, oops. Okay, so that's minus 1/2 if m1 equals 2m2. So let's look at delta V1. So delta V1x, therefore, should be minus 1/2 of delta V2x. Or delta V2x is minus 2 times delta V1x. I guess so we could also say that minus 2 delta V1x should equal delta V2x. Okay. So then afterward, we're going to have V1x final is greater than 0 but smaller. And we're going to have delta V2x is bigger than 0 and it's pretty big. So if you take this arrow minus this arrow, right, so this is final, here's initial, then delta V1 points this way. And then if we look at delta V1x, you could say, and we're going to say if we have delta V2x final minus delta V2x, and so you take this arrow minus nothing, then that is a pretty big arrow that way. So here's delta V2x. And so you see delta V2x is bigger than delta V1x, and they point in opposite directions. So the red cart experiences a change to the right, which is big, and the blue cart experiences a change to the left, which is small. It's only half as big a change in magnitude. Let's watch that. Okay, let's collide the same two carts. So the blue cart has twice the mass of the red cart. So blue cart, 2 units of mass, red cart, 1 unit of mass. But now in the initial state, where the little clock is close to midnight, we will see the red cart moving to the left and the blue cart stationary. So in the initial state, the blue cart has an x velocity of 0, and the red cart has an x component of velocity, which is negative. And then what we're going to see is that after the collision, the red cart will be moving this direction, so this will be bigger than 0. And the blue cart will be moving to the left with a pretty small magnitude, but it'll be moving, here's less than 0, but this is going to be small. And this is going to be going to the right, and it's, well, I guess it's medium size. So then afterwards, the blue cart is kind of like that. It's probably a little smaller, something like that. So to go from nothing to pointing this way is a change, which points this way. And to go from this way to that way is a change, which points that way. And actually, going from this way to that way is a bigger change than going from nothing to that way if these two things are similar in magnitude. So you're going to see that the change in velocity of the red cart is twice as big in magnitude as the change in velocity of the blue cart. But notice that the change in velocity of the blue cart points to the left. The change in velocity of the red cart points to the right. See if you can see that. Because for the blue cart, initial is stationary, final is like to the left. So to the left minus stationary is a change which points to the left. For the red cart, initial points to the left and final points to the right. So right minus left is right minus left is a big change to the right. So the change in velocity for the red cart is a big arrow to the right. The change in velocity for the blue cart is a small arrow, half the magnitude, to the left. Let's watch that. Go this way. The next scenario we're going to watch, so the same two carts. So blue cart has 2 units of mass, red cart has 1 unit of mass. Now they're going to be moving toward each other with comparable speed. But remember, it's kind of like a small truck moving toward a car. So the truck is more massive than the car. So they're moving toward one another at comparable speed, but of course the blue cart will have a bigger momentum than the red cart in the initial state. So, okay, so V1x initial is positive, the blue cart's moving to the right. V2x initial is negative, the red cart initially is moving to the left. After the collision, we will see the blue cart moving to the left, but at a small speed, and we'll see the red cart moving to the right, but at a big speed. So I have a little blue arrow going to the left for the final state, and I have a big red arrow moving to the right for the final state. But again, if you subtract, so I take the final blue state minus the initial blue state. So I take this arrow minus this arrow. So remember, actually, if I were going to take, see, this arrow minus that arrow, if I turn that arrow around, then I get something that points like that. And then by comparison, I take this arrow. Let's say I take this arrow minus that arrow. So I want to subtract that arrow. I turn that arrow around. Then I get something that's kind of like this. That kind of makes sense. So you see, here is a big delta V2 to the right, and here's a small delta V1 to the left, because the ratio of the two magnitudes should be a factor of 2. The less massive vehicle should get the bigger change in velocity. The car should have a bigger change in velocity than the truck if a truck collides with a car. So they're moving toward one another. So they both recoil, but the change in velocity of the one unit of mass is bigger than the change in velocity of the 2 units of mass. And the way we understand that is each one experiences the change in momentum of the same magnitude, because this is a big mass times a small change in velocity, and this is a small mass times a big change in velocity. So those two changes in momentum are equal and opposite. They add up to 0. But if you look at what your eye sees as the changes in velocity, and you see that the red cart experiences a large change in velocity to the right, the blue cart experiences a small change in velocity to the left. This is when they start out moving toward one another at comparable speeds. Let's watch that now. For the next little segment, we're going to stack yet another little block of mass onto the blue cart. So the blue cart will have 1, 2, 3 units of mass, and the red cart will still be just 1 unit of mass. So M1, here's 1, here's 2. So M1 is 3 times as big as M2. And so our first little experiment will have the blue cart moving to the right and the red cart stationary. So V1x initial is positive because positive x-axis is to the right, and V2x initial is 0. Okay, so that is 0, and that is moving to the right. And then what are we going to see as a result? So we're going to see that, so this is a little bit like, well, again, it's kind of like a moving truck hitting a stationary car where nobody is stepping on the brakes, except that the mass ratio now is even bigger, so the change in velocity of cart 2 will be 3 times the magnitude of the change of velocity of cart 1. So I think what we're going to see is after the collision, cart 1 will be moving forward, but it'll be moving forward less quickly, and cart 2 will be moving forward very quickly. Okay? So then what does that look like for a change? So if you take final minus initial, so final minus initial, so we want to negate the initial state, so we reverse its direction. So we take final minus initial, and that looks like a change that points this way, and so it's like pointing to the left, but it's not too big. And then if we take final minus initial for number 2, so final is a big arrow to the right, initial is nothing, so this is a big change to the right. So we have delta V2 is a big change to the right, and delta V1 is a little change to the left. In fact, this change to the left is 1/3 as big as this big change to the right. Let's see what that looks like. Oh, see that? Okay, The next thing we're going to look at, same ratio of masses, 3 units in blue, 1 unit in red. So let's have the blue cart stationary. That means Vx initial equals 0. And let's have the red cart moving to the left. So that means Vx2 initial is less than 0. And the final state, so this is kind of like a lightweight car colliding into a truck, but they both have, like in this case, we've set things up so it's like they both have really springy bumpers and nobody's stepping on the brakes. So we're going to see the little car recoil from the truck, but the truck will also recoil a little bit, because it's pretty massive. So Vx1 final will be to the left, so that's negative, but small. And then we'll see V2x final will be to the right, but big. So we're going to have, in the final state, we'll have the blue cart moving to the left, but with a small velocity. And we'll have the red cart moving to the right, but with quite a big velocity. And then, again, let's try to subtract these arrows. So you see, you take this arrow minus nothing, and you get something that points that way. And then you take this arrow minus that arrow, it's like that. See, it's kind of like that. And then the reverse of that initial arrow, which points to the left, would be something like that, pointing to the right. So again, we'll have a big change in velocity to the right for the red cart, the lightweight cart. And we'll have a small change in velocity, a big change in velocity to the right for the red cart, the lightweight cart, and a small change in velocity to the left for the blue cart, the more massive cart. So let's watch that. Let's look at one more version of the collisions between a blue cart of 3 units of mass and a red cart of 1 unit of mass. So the blue cart has 3 times the mass of the red cart. So I am going to send them toward each other with roughly the same speed. So the blue cart is moving to the right. Oh, whoops. The blue cart is moving to the right. And the red cart is moving to the left. And the speeds I'm going to try to match as well as I can with my hands. And you get kind of an interesting result here. It will turn out that the blue cart will stop dead in its tracks, and the red cart will recoil with an outgoing velocity that is 2 times the magnitude of its incoming velocity. So we start out with 1 unit to the left, and we go out with 2 units to the right. And here we come in with 1 unit to the right, and we go out with 0. So going from 1 unit, so this minus this is a change that looks like that. And this minus this, so to subtract that, we put this on the end. And so that's a change that looks like that. So this change has 3 times the magnitude of this change. So I think that makes sense. Since this mass is 3 times as big as this mass. So if this velocity change is 3 times as big as this velocity change, then because of their ratio of masses, this momentum change is the same in magnitude as this momentum change, but of course they're in opposite directions. Yeah. So this is 3 units of velocity change to the right for the red cart. This will be 1 unit of velocity change to the left for the blue cart. Although equivalently, the momentum changes are the same magnitudes and opposite directions. So let's see what that looks like. Now let's go back to equal masses and let's watch a different kind of interaction. Let's watch the 2 carts push away from each other. So it's kind of like if you and I are both on roller skates and we start out with our hands kind of clasped like this and push against each other. So what's actually going to happen is I have the blue cart here, the red cart here. Each one has 1 unit of mass, and there's a little coiled up spring in between them. And then we release that little coiled up spring. And we'll see how that works a couple chapters from now. But basically, there's some kind of, the result of releasing the coiled up spring is that the two carts push away from one another. And because they have the same masses, and initially they both have 0 momentum, right? So there's 0 velocity, therefore 0 momentum. And the total of the two momenta is 0 initially. So each cart is not moving. The system is not moving. So initially V1x initial is 0, V2x initial is 0. They push away from each other. So if the red cart moves to the right with 1 unit of velocity, then to conserve momentum, the blue cart moves to the left with 1 unit of velocity. So this final blue arrow points to the left and it's 1 unit long, and this final red arrow points to the right and it's 1 unit long, representing the two velocities. So that's a change in velocity. So this minus 0, so this is the initial state here, and this is the initial state here. This is kind of like a motion diagram, by the way. Last time I think I told you that motion diagrams weren't very useful to me. This is kind of a motion diagram. So here's time 0, and I'm showing them not moving. And here's some later time, and I'm showing them moving away from one another. That's about as fancy as my motion diagrams get. So this final minus initial looks like this for cart 1, the blue cart, and final minus initial looks like this for cart 2, the red cart. And so you can see that M1 times delta V1 plus M2 times delta V2, they add up to 0. That kind of makes sense. So you can also see, right, the ratio of these two changes in the x direction in velocity is -1, since M2 over M1 is 1. Okay, let's see what that looks like. Let's look at the same thing now for the case where we add an extra unit of mass to the blue cart. So now the blue cart is 2 units of mass, the red cart is 1 unit of mass. They both start out at rest, and they're connected by a compressed spring, and then I release the spring and they push apart from one another. So the change in velocity of the blue cart will be -1/2 the change in velocity of the red cart, since the blue cart has twice the mass of the red cart. And they both start out at 0. So in the final state, the blue cart's velocity will be this little arrow to the left, and then twice as big as that to the right will be the red cart's velocity. So if the red cart has 1 unit of velocity to the right, then the blue cart has a 1/2 unit of velocity to the left. So delta V1x looks like this little arrow to the left, and delta V2x looks like this big arrow to the right. And then let's see what that looks like. If I make the blue cart twice, if I make the red cart twice as massive as the blue cart, then you can hear them reach the ends at different times. What if we make the distances that they have to travel a ratio of 2 to 1? So you see the blue cart will have to travel twice as far as the red cart will to hit the end. Then I think your ear will detect that they hit the ends at the same time. Let's see how that goes. Yeah. So you can see the blue cart travels twice as much distance as the red cart does after they separate, which confirms the idea that the speed of the blue cart is twice the speed of the red cart after they separate. I'll bet you guessed what's coming next. So let's do the same thing now, but with a 3 to 1 ratio of mass. So now tripled the mass of the blue cart by loading 2 little bricks into its little payload area. So 3 units of mass for the blue cart, cart 1, 1 unit of mass for the red cart, cart 2. They start out both at rest. They're squished. They have a squished together spring. So they're going to push apart. So the change in velocity for cart 1 in the x direction will be minus 1/3 the change in velocity of cart 2 in the x direction. Since they both start out at 0, so the final velocity of the blue cart will be this little arrow, let's say 1 unit long, to the left. And the final velocity for the red cart will be this big arrow, let's say 3 units long, to the right. So then this minus 0 is like that, and this minus 0 is like that. And again, if you multiply this by its mass, and you multiply this by its mass, then you have 2 arrows that sum to 0. In other words, the changes in momentum sum to 0. So let's watch that. And then we can make the ratio of masses be 3 to 1. So the red cart will be 3 times the mass of the blue cart. And then we can position them in such a way that the distance that the red cart has to travel is 1/3 of the distance that the blue cart has to travel. Here, again, I have to level out the track. Okay, and let's try that. That's pretty good. Not bad. Okay. So now that we've gone through those examples of collisions between objects, sometimes of the same mass, sometimes of a ratio of masses of 2 to 1 or 3 to 1, and in every case it's been an isolated system of 2 objects interacting only with each other. That was on the little rolling carts on a track. You will actually do something very similar on a you will actually do something very similar with little rolling carts on a track in class on Wednesday. So that's after we've gone through chapter 5. So this will be chapters 4 and 5 together. Meanwhile, let's move on to the air track. That's just like the air hockey table. And the air track will not be tilted this time. It will be a level air track. So we're going to have the level air track. So we're not studying acceleration anymore. Now we're studying momentum. So the air track will be level. We're going to collide pairs of carts on the air track. And we're going now to look at graphs of velocity versus time for cart 1 and for cart 2. And sometimes their masses will be the same and sometimes they'll be different. So we're going to go through an exercise very similar to what we just did a moment ago. But we're going to use graphs of the initial state and the final state and see if we can understand which graphs make sense to describe the motion of the 2 carts. To be a little bit more quantitative about pairs of carts colliding, I've made some graphs and combined it with some video clips of the air track. It's basically like an air hockey table for physics courses. And so what you're going to see in the clip is cart 1 will initially be moving to the right, and cart 2 will initially be stationary. They're going to collide, and it looks as if after they collide, cart 1 stops dead in its tracks, and cart 2 continues, and in fact cart 2's outgoing velocity seems to be the same as cart 1's incoming velocity. And by the way, if you like to play pool, that's exactly what you see when you hit a stop shot playing pool. You hit the cue ball directly into a target ball in such a way that where the cue ball is basically sliding, not rolling. So we want to look for graphs, I guess, that match the initial conditions and also match our observations. So let's first pause and watch the clip. Yeah. And then it seems as if if graphs A and C are not compatible with what we see in the clip because they seem to represent an initial state where the two carts are moving toward one another. And that's not the initial state we have. The initial state we have is where cart 1 is moving toward a stationary cart 2. By the way, each one of these graphs has velocity, the x component of velocity on the vertical axis, and I've tried to label key features here. Like here's -1 meter per second, there's +1 meter per second, here's -1 meter per second, plus second. And then there's time on the horizontal axis. And if you want to see these graphs more clearly, you can look at the PDF slides at phys8slides04.pdf in the course files area. So for two carts of equal mass colliding, we expect the change in velocity in the x direction for cart 1 to be the same magnitude but the opposite sign as the change in velocity in the x direction for cart 2. So delta v1x over delta v2x is minus m2 over m1 minus 1 if the two masses are the same. So then we can look at the graphs, and let's look at graph B here. So cart 1 goes from +1 meter per second to minus 0.3 meter per second. That looks like a change of minus 1.3 meter per second. And then cart 2 goes from 0 meters per second to plus 0.7 meters per second. So that looks like a change of plus 0.7. So the changes do indeed have opposite sign, but it looks like the change for cart 1 is twice as big, approximately, as the change for cart 2. That would only make sense if cart 2 had twice the mass of cart 1. But we said that the two carts have the same mass, so we can rule out B. Seems like we're going to want D here. So cart 1 goes from +1 to 0 meters per second, and cart 2 goes from 0 meters per second to +1 meters per second. And so this is a change of -1. This is a change of +1. That makes sense. They have the correct ratio of -1. It's also consistent with what we saw in the video. So I think I like D, delta, for this one. Let's watch the clip one more time and next example. Let's look at a second example with that same combination of masses. So the two carts are equal mass, but now they will initially be moving toward one another, like that. So cart 1 is moving to the right initially, cart 2 is moving to the left initially, and I guess we can see which of these graphs match those initial conditions. It looks as if graph B does not, because cart 2 is initially stationary. Graph D seems to match the initial conditions. Graph C does not match the initial conditions. It has cart 2 initially stationary. So I guess it's either A or D. And, well, we could watch the clip first, or we could see what we think we expect, or see we could. So this seems like a change of -2 units, from +1 to -1 meters per second for cart 1. For cart 2, it looks like a change of +2 units, +2 meters per second, from -1 to +1. So it seems like the ratio of the two changes in velocity in the x direction correct. It's a ratio of -1, ratio of minus m2 over m1. Let's look at number D here and see if that makes sense. So cart 1 goes from +1 to -1.7. So that's a change of -2.7 meters per second. Cart 2 goes from -1 to +0.3. That's the change of +1.3. +1.3 minus 2.7. So that would seem to be correct only if cart 2 had twice the mass of cart 1. But we're told that the two carts are equal mass, so I think we're going to rule out D. So it seems like what we expect to see is that after the collision, cart 1 will be moving to the left, and cart 2 will be moving to the right, and the two carts will, it seems like they'll essentially just trade initial velocities. And yeah, let's watch the clip. So it does seem from the clip that the two carts did, in this case, basically just trade initial velocities. That, it turns out, that's what happens when you have a direct hit between two objects of equal mass if, as we'll see in the next reading, no energy is lost in the collision. So we'll call that next time an elastic collision. In any case, we did see that the two carts basically traded velocities, and that's consistent again with graph A alpha. For our next example, let's look at a collision between two carts of different masses. So cart 2 will be twice the mass of cart 1. So I drew cart 2 a little bigger than cart 1 to make it visually obvious. I guess this is, again, maybe this is a motion diagram. So cart 1 initially is moving to the right. Cart 2 initially is stationary. The question is, what do we expect after they collide? Let's see if we can rule out any of these graphs. So cart 1 initially moving to the right, cart 2 initially stationary. It could be A. It cannot be C because it doesn't match our initial conditions. I guess A, B, and D match the initial conditions, so we can rule out C. And then, if we look at A, cart 1 goes from plus 1 to plus 1 to plus 0.3. That's a change of minus 0.7 meters per second. Cart 2 goes from 0 to plus 1.3. That's a change of plus 1.3. So if we ignore the rounding, then minus 0.7 versus plus 1.3 seems to be a ratio of 2, but it's in the wrong direction, because this seems like what you would expect if cart 1 were twice the mass of cart 2. I think we can rule out A. Let's look at B. So it seems like cart 1 goes from plus 1 to minus 0.9. That's minus 1.9 meters per second. Cart 2 goes from 0 to plus 0.2. So that's kind of like a 10 to 1 ratio of change, right? So that's like, see, delta V1, like almost minus 2. Delta V2 is like about plus 0.2. So that seems like this would make sense if cart 2 were 10 times as massive as cart 1. Cart 2 is more massive than cart 1, but not by a factor of 10. It's only a factor of 2. Let's look at D here, delta. So cart 1 goes from plus 1 meter per second to minus 0.3 meter per second. So that's a change of minus 1.3 meter per second. Cart 0 goes from 0 to plus 0.7. Again, if we ignore the rounding, and that's a change of plus 0.7. That's a change of, let's say, minus 1.3, minus 1.4. I think that makes sense because the change in velocity for cart 1 is twice the magnitude of the change in velocity for cart 2, and of course they're in opposite directions. That makes sense because the less massive cart should experience twice as large magnitude a change of velocity. So I guess if we want to draw the final state here, it seems like what this depicts is in the final state, cart 1 recoils backwards, so it's going about a third as fast backwards as it was initially going forward. And cart 2, initially at rest, is now going at something like 2/3 speed at which cart 1 was initially going. So let's now look at the clip and see if it looks like this picture. So we will take some little masses and put them onto the red cart. So now we've doubled the mass. So I think the clip does look like this picture. So I think that's pretty good. In the final state, cart 1 is going backwards, maybe about a third the speed it was initially going, but in the opposite direction. And cart 2 is now going to the right, but with a final speed that is maybe 2/3 of the initial speed of cart 1. By the way, for this collision that we just watched, where cart 2 has twice the mass of cart 1, and cart 1 is initially moving to the right, and cart 2 is initially stationary, the graph that we chose was this graph. Now it's drawn a little bigger. So here's the x component of velocity measured in meters per second on the vertical axis. Here's time measured in seconds on the horizontal axis. And cart 1 went from +1 meter per second down to minus 0.3 meter per second. And cart 2 went from 0 meter per second up to plus 0.7 meters per second. And you can see that the change in the yellow curve has twice the magnitude of the change in the blue curve. So the change in velocity for cart 1 had twice the magnitude, and of course opposite direction, of the change in velocity for cart 2. And that makes sense. It's the ratio of the two masses. Now, the question is, if we drew momentum on the vertical axis instead of drawing velocity on the vertical axis to describe this collision, would the yellow and blue curves have this ratio of changes that's different from 1, or would the change in momentum for the first cart be the same in magnitude as the change in momentum for the second cart? So think about that, and I'll show you the graph on the next page of momentum instead of velocity on the vertical axis. Looking instead at a graph of momentum versus time instead of velocity versus time. So we have the x component of momentum on the vertical axis, and momentum has units kilogram meters per second. Then we still have time on the horizontal axis. So we see cart 1 goes from +1 kilogram meter per second down to minus 0.3. That's a change of minus 1.3 kilogram meter per second. And cart 0 goes from 0 up to plus 1.3. So that's a change of plus 1.3 kilogram meters per second. So cart 1 experiences a change of minus 1.3. Cart 2 experiences a change of plus 1.3. The two changes are equal and opposite. So that makes sense. The momentum lost by cart 1 equals the momentum gained by cart 2. The sum of the two momenta is the same before and after the collision. This is what you expect from the collision of two objects that form an isolated system. In other words, the collision of two objects that interact only with one another. Total momentum before equals the total momentum after. Therefore, the change in momentum of one cart must be offset by the change in momentum of the other cart. So the two changes must sum to 0. And then you can sort of see where the average of these two curves is. So you know take the average and you double it, you get the sum. So you say, okay, see here's 0 plus 1. So 0 plus 1 is 1. And here's minus 0.3 plus 1.3 is 1. So the sum of the two curves starts out there, and the sum of the two curves lands exactly where it was before. So you can see the sum of the two curves is the same before and after. Easier way for your eye to see that is that the average of the two curves is the same before and after. The average is proportional to the sum. So again, the change in P sub x for cart 1 is negative, the change in p sub x for cart 2 is positive, and those two changes have the same magnitude. Because momentum is a conserved quantity, and because this is an isolated system. Therefore, momentum is constant for this system. Now let's consider a collision between the same two carts. So cart 2 has twice the mass of cart 1. But initially, cart 2 is moving to the left, while cart 1 is stationary. So let's see which graphs match those initial conditions. Cart 1 should be stationary. Cart 2 should be moving to the left. So I think B matches those conditions. And I think A matches those conditions. I think C matches those conditions. So D does not, because D shows cart 1 moving to the right, cart 2 moving to the left. Okay, so it seems like it's A, B, or C. And now we know the ratio of changes in velocity should be the reciprocal of the ratio of masses. So if we look at A, it looks like cart 1 goes from 0 to minus 0.7 meters per second. Cart 2 goes from minus 1 to plus 0.3. So that's a change of minus 0.7 and a change of plus 1.3. That's a 2-to-1 ratio, but it's in the wrong direction because it shows the more massive cart having the bigger change in velocity. That doesn't make sense. If you look at B, we have cart 1 undergoes a change of minus 1.3 meters per second. So that's from 0 to minus 1.3. Cart 2 undergoes a change from minus 1 to minus 0.3. So that's plus 0.7. Minus 1 to minus 0.3 is plus 0.7. That's plus 0.7. That's minus 1.3. That seems to be a 2-to-1 ratio in the correct direction. So I think I like B. And let's just look at D to let's just look at C to be sure. We were pretty sure we liked B, but let's look at C. So cart 1 goes from 0 to minus 1.8 meters per second. That's a change of minus 1.8. Cart 2 goes from minus 1 minus 0.8 meters per second. That's a change of plus 0.2. So that would seem to be like a 9-to-1 ratio of masses. So this is what you would see if cart 2 were 9 times as massive as cart 1. Cart 2 is more massive than cart 1, but it's not 9 times as massive. It's only 2 times as massive. So I think I like B. So then what B would look like in the final state seems to be cart 1 is moving backward, and it's moving backward faster than cart 2 initially was moving backwards. So cart 1 will be moving to the left at a bigger speed than cart 2 was initially moving to the left. Cart 2 will also be moving to the left, but I guess with about a third of it. Like this. So cart 2 should continue moving to the left, but its final speed should be about a third of its initial speed. Cart 1 should moving to the left the speed that is a little bigger than cart 2's initial speed. That seems to be a way for us to conserve momentum. Collision where cart 2 has twice the mass of cart 1 and cart 2 is initially moving to the left and cart 1 is actually stationary. Now let's watch the clip. Again, I think the clip matches the graphs, matches graph B. The next example will use the same two carts. So cart 2 has twice the mass of cart 1, but now they start out moving toward one another. And let's see what we expect. So we're going to try to make them move toward one another with similar initial speeds. And again, let's look at the initial conditions. So plus 1 and minus 1, plus 1 and minus 1, plus 1 and minus 1, plus 1 minus 1. They all seem to match the initial condition, so we can't rule anybody out that way. Now, the change in velocity for cart 1, the less massive cart, should be twice the magnitude course in the opposite direction of the change in velocity for the more massive cart. So let's see what we have here. So if we look at A, we go from +1 to minus 0.3. That's a change of minus 1.3. Here we have it go from -1 to plus 1.7. That's a change of plus 2.7. But that seems like the right ratio, but the cart 2 has the bigger change than cart 1 magnitude. That doesn't make sense because cart 2 is more massive. Massive cart should have a smaller change in velocity. Let's look at B. So it seems like cart 1 goes from, this looks like about -2, sorry. Goes from roughly +1 to -2 meters per second. So that's a change of about -3. And then it seems like cart 2 goes from -1 to -0.2. So that's a change of about plus 0.8. So there's plus 0.8 and there's about -3. So that seems like about a 4-to-1 ratio of mass. So it does have cart 2 more massive than cart 1, but by like a ratio of 4-to-1, which is not consistent with our problem statement. And then we can look at C. So there's +1 down to -1. It's a change of -2. -1 up to +1 is a change of +2. C is what we would expect if the two carts had equal mass. They do not have equal mass. Let's look at D. So +1 down to -1.7. That's a change of -2.7. And then -1 up to +1 plus 0.3 is a change of plus 1.3. So this is -2.7 and plus 1.3. So within rounding errors, that makes sense. So it seems like what we expect to see, so the change is twice as big in magnitude for cart 1, lighter cart, half the magnitude cart 2, which is the more massive cart, by a factor of 2. So it seems like in the final state, cart 1 is going backwards with almost twice its initial speed. And so it really recoils backwards. And in the final state, cart 2 is going forward, that's to the right, with about a third its initial speed. So it's something like that. So let's see if that's consistent with the clip. Let's watch the video clip. Okay, so I think that's what we saw. So it seems like what we saw, was, consistent with D, delta. So it seems like we went from +1 to -1.7, part 1, and part 2 went from -1 to plus 0.3. So the change in velocity for cart 1 had twice the magnitude of the change in velocity for cart 2, consistent with cart 2 having twice the mass of cart 1. Which has more momentum? A 0.5 kilogram baseball pitched at 40 meters per second, or a 0.010 kilogram bullet fired at 400 meters per second. Okay, so a half kilogram baseball versus a 10-gram bullet, but it seems like there's a factor of 10 ratio of speeds. So let's see if we can work that out. Well, we could kind of, by the way, what is momentum? Momentum is what times what. So momentum is mass times velocity, but we just want the magnitude. So the magnitude of the momentum is the mass times the speed. And so in one case, so it seems like the bullet is going 10 times as fast as the baseball, but the baseball seems to have 50 times the mass of the bullet. So I think the baseball is going to have more momentum, but let's see. So for the baseball, we have P is mv velocity, which is 0.50 kilograms times 40 meters per second, which is 20 kilogram meters per second. And for the bullet, we have 0.010 kilograms times 400 meters per second, which is, so it's 400 divided by 100 is 4 kilogram meters per second. So indeed, the baseball has the bigger momentum. One way to measure the speed of a bullet is to fire the bullet at a wooden cart of known mass, which is initially at rest, and then measuring the speed of the cart with the bullet embedded in the cart. So the figure shows a 0.0100 kilogram bullet, that's a 10 gram bullet, fired at a 4 kilogram cart. After the collision, the cart rolls to the right at 2 meters per second. What is the bullet's speed before it strikes the cart? So the key here is that the bullet plus cart system is isolated. So the bullet and the cart interact only with each other. That's at least a true statement in the horizontal coordinate. And so we can say that the total momentum of the bullet plus cart system before the collision is the same as the total momentum of the bullet plus cart system after the collision. And then there's a very convenient fact here, and again, you'll see this in more detail in chapter 5, but in the case where things collide and stick together, then you know the velocity of the two things is the same. In other words, after the collision, the velocity of the cart and the velocity of the bullet are the same because they stick together and they're moving together. So that makes life easy for us. So let's say the initial state, here, let's draw a little textbook style clock here. So here's the initial state. So we have, so you say let m equal 0.010 kilogram, that's the bullet. Then let big M equal 4 kilograms, that's the cart. And we know that V initial of the bullet, in the notation used in Eric's book, which is not the same, we would call one of these objects 1 and one of them 2. I'll use 1 for the bullet and I'll use 2 for the cart, but I'll stick with the picture using a capital M here. So we have V1x initial is unknown, and we have V2x initial is 0. So I guess we have the bullet, which is moving at some large unknown speed, and then we have the cart, which is at rest. And then in the final state, we have the bullet and the cart together. So here is the cart with the embedded bullet, and it seems like this speed has to be a little slower. Actually, it could be a lot slower, right? So the speed is going to be a lot slower than that initial speed because the bullet is 400, the cart is 400 times the mass of the bullet. This is going to be much, much slower. So actually, here, let's draw a teeny little line, little arrow here. Yeah, so we have d1xf equals d2xf equals 2.0 meters per second. Yeah, okay, so now we can use our momentum equation. So this is the equation you'll use for all problem solving with momentum if you have just two objects colliding. So it's m1 v1xi plus m2 v2xi equals m1 v1xf plus m2 vxf. Now, in this case, the equation simplifies right away because object 2 initially is not moving, so we can get rid of that one term. And then also, the final speed is the same. So actually, we'll just give that a name. We'll just call that dxf. Okay, so there's only one final velocity. It's like the same final velocity for both of them. So we have m1 v1xi equals m1 plus m2. Here, I'll make the second m big just because the diagram did. dxf. So actually, now all we have to do is divide both sides by m1, and I think we're done because we just want to know this unknown, v1xi. So that gives us v1x initial, that's the initial speed, the initial x component of the velocity of the bullet is m1 plus m2 over m1 times vx final. And that is, so m1 plus m2 is going to be 4.01 kilograms. And m1 is 0.01 kilograms. And this is 2 meters per second. So this is like 4 times 2 divided by 0.01. That's like 4 times 2 times 100. 400 times 2, that's like 800, right? So that's basically 800 meters per second. Actually, I guess we could do a little better because it's 4.01. It's actually 802. Okay, so if we really want to be a little more precise, I guess 401 times 2 is 802. So it's 802 meters per second. But we could probably, 800 is probably close enough. Oh, here we go. Ha! So the answer is Charlie, 800. Oh, no. Oh, look at that. The answer is delta, 802 meters per second. Okay, I guess I did have to be careful with the math. So 802 meters per second. That's our first quantitative problem using momentum. Isn't that fun? A final exam problem used in this course about 6 or 8 years ago started like this. You have been hired to check the technical correctness of an upcoming made-for-TV murder mystery. The mystery takes place in a space shuttle. Oh, well, there used to be a space shuttle. Maybe it takes place now in the International Space Station. In one scene, and maybe it actually takes place in a tech billionaire's spacecraft now once it achieves ongoing orbit, but I digress. In one scene, an astronaut's safety line is sabotaged while she is on a spacewalk, so she is no longer connected to the space shuttle. She checks and finds that her thruster pack has also been damaged and no longer works. She is 200 meters from the shuttle and is moving with the shuttle. That is, she is not moving with respect to the shuttle. There she is, drifting in space, with only 4 minutes of air remaining. To get back to the shuttle, she decides to unstrap her 10-kilogram toolkit and what does she do with it? What does she do with her 10-kilogram toolkit? Well, now that you are an expert at momentum, you know that she should throw her 10-kilogram toolkit with all her might. Now she wants to move herself toward the space shuttle. So which way should she throw her 10-kilogram toolkit? I think she should throw her 10-kilogram toolkit with all her might away from the shuttle, and then she will recoil toward the shuttle. And then the question is whether she can throw the toolkit at a high enough velocity away from the shuttle that she then makes it back to the shuttle before her 4 minutes of remaining oxygen run out. So we won't worry about that part, but you know this is again a momentum problem. So I guess you could say 1 equals astronaut and 2 equals toolkit, and you would say m. Well, now you know that both have an initial speed of 0, initial velocity of 0. So see m1, oops, m1 v1xi plus m2 v2xi. Well, initially neither one of them is moving, so this is easy, that's 0. And then that equals m1 v1xf plus m2 v2xf. So initially this is 0 and this is 0. And so then you get that her final, so you get, and she is the astronaut. So v1xf, that's the astronaut's final velocity in the x direction, is minus m2 over m1 times v2xf. And do we know how massive she is? No. I guess we would need to know her mass also. Okay, so let's suppose that the astronaut's mass is, well, she's wearing a spacesuit. So maybe she, I don't know, let's say she's 70 kilograms with a spacesuit. And 2 is the toolkit. Yeah. So you see, this would be like minus, let's say toolkit is 10 kilograms. And then let's say the astronaut without the toolkit, but with her spacesuit, let's say is 70 kilograms. And then how fast can she throw it? Well, this is however fast she throws the toolkit. And then her final speed, her final velocity toward the space shuttle. So it seems like her final velocity toward the space shuttle is something like 1/7 of the toolkit's velocity away from the shuttle, if, assuming this ratio of masses. So that's the idea. Okay, that's the premise of the problem. That's how you would work it out. And then there's, in addition, some constant velocity calculation where you have to figure out whether she makes it 200 meters in 4 minutes. So again, this equation gets us very far in chapter 4. By the way, in the old days, I would use this as a segue into something that you already saw, where 2 carts of different masses separate from one another with kind of an explosive way when a spring releases. So I'll just show you again, just for fun, a 3-to-1 ratio of masses, even though we probably expect something like a 7-to-1 ratio of masses for the astronaut and her toolkit. And then we'll move on. Couple things that Eric's book does really well in this chapter. One of them is introducing the concept of a system, and another is introducing the concept of a conserved quantity. And it turns out that all conserved quantities in physics are extensive quantities. Maybe there are some extensive quantities that aren't necessarily conserved, but all conserved quantities are extensive. And so what is an extensive quantity? It's kind of a detail. You don't really need to know what an extensive quantity is, but a lot of people ask about this. So if a quantity Q describing a system is extensive if, when you divide up the system into 2 parts, Q of part 1 plus Q of part 2 equals Q combined. So in other words, so you could say like money in the bank has this property. So if you divide up your pile of cash into two parts, and one part goes into your checking account, one part goes into your savings account, say what's my combined amount of money? It's the money in account 1 plus the money in account 2. So a lot of things have this property, like the mass of stuff, as long as there's no nuclear reaction happening. Or it's often true of the volume of stuff, although that can sometimes not be true if like there's a chemical reaction that causes things volumes to change. But often it's usually true of volume. I have a room of so many cubic meters, and I have another room of so many cubic meters, and I say, what's the combined volume? It is the sum of the two volumes. So I guess that does tell you the volume is extensive, but it's not necessarily conserved, because there could be chemical reactions that change the volumes of things. Yeah, money is extensive. It's not necessarily conserved, because there could be inflation, or there could be compound interest, or there could, but anyway, but it is extensive. You have two amounts of it, then you say how much is the total, you just add the numbers together. It's true for mass, it's true for number of atoms. Some counter examples, things that are not extensive quantities. Humidity is not an extensive quantity. So let's say I'm in the house and there's 20% relative humidity. Maybe I keep the air conditioning really cranked up, and I go outside and it's 80%. Let's say I'm inside and it's 30% relative humidity. Outside there's 90% relative humidity. And I say, well, what happens if I open the door? I'm not going to get 120% relative humidity by adding the two. It doesn't make any sense. Density. I might say, well, okay, I have water, density 1 gram per cubic centimeter, and I have some rock, let's say density 2.3 grams per cubic centimeter, and then I put the rock into the water. I don't have 3.3 grams per cubic centimeter. That doesn't make sense. Or color. I don't know. You say, color. You have to ask how you're going to quantify color. Temperature, I have like one object at, 50 degrees Celsius, another object at 60 degrees Celsius. If I combine them, I don't get 110 degrees Celsius, okay? So some extensive quantities are conserved, only a few. Meaning you can, a quantity which is conserved can be transferred from one object to another, but it can never be created or destroyed. Momentum, and then in chapter 5, energy, are examples of conserved quantities, physics. All conserved quantities are extensive, but only a few extensive quantities are conserved. And again, if this point really confuses you, just don't worry about it, but it is something that people tend to ask about, so I want to go through it a little bit. For instance, how about number of dots? Is number of dots an extensive quantity? I think so, because look, I've got this many dots over here, 10. I've got, let's say, 15 dots here, and I say, what's the total number of dots? It's like, let's say, 25 dots. So I'd say yes, number of dots is an extensive quantity. How about dot diameter? Oh, well, here I have, let's say, dot diameter of 1. Here I have dot diameter of 1. If I combine the two pictures, do I get dot diameter of 2? No. Dot diameter is not an extensive quantity. No. How about total area covered by dots? Well, if I add up the total area covered by dots over here, and I add up the total area covered by dots over here, then I think I can add those and I get the total area covered by dots. That seems fine, although you could, if you want to be really careful, you'd say, well, as long as the dots don't overlap. Like if the dots, if I take these dots and overlay them on these dots, if some of them overlap, then that might change the total area covered by dots to be different from just the sum of the two. But if you leave out that possibility, you say, well, okay, so I say yes, as long as the dots can't overlap. Okay, see? This is a little kind of a digression. So, but I think you're going to have one upcoming worksheet question. And there's just one little part of one worksheet question. This is only one little part of one question, but there's an example of a velocity versus time graph. And you'd say, okay, the velocity versus time graph below shows the motion of two different objects moving across a horizontal surface. Could the change in velocity versus time be attributed to friction in each case? We don't know anything about friction yet in this course, really, except we know that friction tends to slow things down with respect to one another. That's all we know at this stage. So this is, here's 0. This is velocity. And here's negative velocity. And here's positive velocity. So maybe it's the x component of velocity. And here's time. So we have time on the horizontal axis. We have velocity, the x component of velocity, on the vertical axis. And then you'd say, well, what is friction, especially if it's friction for something sliding across a surface? You know, so I have a surface here, then I have an object which is moving, and if there's friction, what does friction do? It makes the object slow down, right? And so if it's moving this way, then friction tends to cause it slow down. If it's moving this way, friction also causes it to slow down. So friction reduces the speed, right? It reduces the magnitude of the velocity. So friction can cause a decrease in the magnitude of velocity. Friction can decrease speed. What's happening here? In this case, this object, is it speeding up or slowing down? Well, its speed seems to be getting bigger, right? The magnitude of its velocity is getting bigger. So this cannot be due to friction, because it's speeding up. Friction would not cause something to speed up unless maybe it's on a conveyor belt and it can catch up to the conveyor belt. But if it's on a stationary horizontal surface, friction will not cause it to speed up. What about here? This object seems to be slowing down. You see it's moving backwards, and now it's moving backwards less quickly, it's moving backwards less quickly, it's moving backwards even less quickly. Eventually it seems like it's going to stop. So this is slowing down, whereas this is speeding up. So friction is not going to cause something to speed up, except in the weird case where, like, you drop it onto a conveyor belt and then it catches up to the conveyor belt. But again, if you're talking about an object sliding across a stationary surface, friction will cause something to slow down. It will not cause something to speed up. So I would say no for the top curve, yes for the bottom curve. So I think I like B here. So this could be attributed to friction, because friction can slow something down. That's all. Here are the key results for Chapter 4, the momentum chapter. Okay, so momentum is mass times velocity. Velocity is a vector. Mass is a scalar. If you take a vector, you multiply it by a scalar, you get another vector. So momentum is a vector. Momentum points in the same direction as velocity. Although the units of momentum are kilogram meters per second, units of velocity meters per second, because the units of mass are kilograms. One dimension will just deal with the x component. P sub x is m times v sub x, the x component of momentum, the mass times the x component of velocity. You'll see Eric say inertia, writes m for mass. But inertia is, if you have an isolated system of two objects, that means two objects that interact only with each other and not with anything else, you can say the total momentum in the x direction before the interaction equals the total momentum in the x direction after the interaction. So you say, okay, mass times velocity in the x direction plus mass times velocity in the x direction for the initial state equals that same sum for the final state. So you solve problems with momentum, do a few of them in worksheet 4. You'll write down this equation probably half a dozen times. M1 V1x initial plus M2 V2x initial equals M1 V1x final plus M2 V2. If you define delta V1x to be V1x final minus V1x initial, and you define delta V2x to be x final minus V2x initial, and you solve for delta V1x over delta V2x, you get minus M2 over M1. This This is useful for problem solving. This is useful for looking at those graphs of two things colliding and seeing what makes sense. So the ratio of the two changes in velocity should be a negative number because they should be in opposite directions. And it's the reciprocal of the ratio of masses. If you happen to have a non-isolated system, and if you happen to know how much momentum enters or leaves the system across the system boundary, then the final momentum minus the initial momentum of a system due to some interaction is given this symbol J for impulse, Eric's book. But we will almost never quantify impulse except to be able to argue that it equals 0. So if no momentum enters or leaves a system, it is true if you have an isolated system. An isolated system, the constituents of the system interact only with one another and not with anything outside the system. Then the total final momentum of the system equals the total initial momentum. Final minus P initial is 0, so there's 0 impulse. So in pretty much the only time you'll ever use impulse is just to say that it equals 0 because it's isolated. But it's in the book, so I want to mention it. By the way, at this stage, do you remember the key results from chapter 3 for acceleration? They might be worth writing down. So see if you can remember them with me, the key results from chapter 3. So I think chapter 3, acceleration, these are the small number of results worth remembering. One, this is really from chapter 2. V sub x is dx by dt. The x component of velocity is the rate of change of the x coordinate. And then we have a sub x is dv sub x by dt. So the x component of acceleration is the rate of change of the x component of velocity. Or we could write it in vector form. Well, you don't like it if I write it in vector form. I could say a with an arrow is the time derivative of v with an arrow, but let's not do that. And then if a sub x is constant, then we have dx final equals dx initial plus a sub x t. And we have x final is x initial plus d sub x initial t plus 1/2 a sub x t squared. And then if you solve this equation for t and then plug that t into this equation, what you get is vxf squared equals vx initial squared plus 2 a sub x times x final minus x initial. And I guess two other results are that for free fall near Earth's surface, we have the x-axis pointing up, and we have a sub x is minus g. And for frictionless sliding with negligible friction down an inclined plane, we have the x-axis points downhill, and a sub x is plus g sine theta, where theta is the incline angle of... That's not very readable. Theta, x points, a sub x is plus g sine. Those are all the key results from chapter 3. And then this and this are really the only two key results, well, and this definition for chapter 4. I think we might work one more example problem By the way, so we're going very quickly through the early chapters of Mazur's textbook. So chapters 1 through 9 go pretty quickly. We're going to slow down for the more difficult topics. Chapters 10, 11, 12 will be the most difficult part of the course, so we'll take a lot more time per chapter when we get there. So we're doing a faster pace now so that once we get through Mazur's chapter 12, which is about torque, then we can take our knowledge of vectors, forces, and torques and use them to learn some things about architectural structures. So I hope that's one of the key features that make this course fun. But now let me cook up one example problem. You don't have to watch this if you don't want to, but I think it'll kind of help you if you want a little more quantitative, you want a little more to know about how we're going to solve problems using results from momentum. Okay, here is an example problem I'm kind of putting together from my head. So the classic problem is two male moose of different masses. So you have a moose of mass m1, a big moose of mass m1, and a little moose of mass m2. And they're charging one another on a sheet of icy tundra. Why is it icy tundra? Icy so that we can say friction is negligible. We're going to say friction is negligible so that we then say there's no horizontal interaction with the ground, and then the moose plus moose system is an isolated system. See? So two male moose charge in opposite directions toward one another at the same speed, but in opposite directions on an icy patch of tundra. So in the initial state, we have a big moose moving to the right with speed v initial. We have a little moose moving to the left at speed v initial. So these are the same speed, but of course in opposite directions. Then their antlers lock together, and this tangle of moose antlers and legs and arms goes sliding together across the tundra. Of course, which direction does it slide? Well, if these, you see that this moose has a bigger momentum to the right compared to this moose's momentum to the left. You see, this moose's momentum to the right is bigger than this moose's momentum to the left because it's the same speed, but the big moose has a bigger mass. So the total momentum of the moose plus moose system points to the right in this initial state. So therefore, the total momentum of the moose plus moose system will point to the right in the final state. Final state, the moose's antlers are locked together. So the two mooses, the two mooses move at the same speed. It's the same v final, but they're locked together. They move together. And I'm going to say, well, so the problem actually is a little bit different. The problem is that you know the final speed and you want to predict the ratio of the masses. But I'm going to say that m1 equals 2 m2, and we want to know what is v final compared to v initial, okay? And let's say v initial is 10 meters per second, okay? And the question is, what is v final? All right. I'm changing the problem a little bit. So we're going to say that the total momentum, so the total final momentum equals total initial momentum because this is in the x direction. The x direction because the system consisting of the two mooses is horizontally isolated, okay? We only care about the x coordinate. So as far as the x coordinate goes, the two mooses interact only with each other and not with anything else, because the ground is slippery, so there's no friction. So we're going to say that in the x-coordinate, the two moose system is isolated in the x-coordinate. So the total momentum in the x direction after they collide is the same as the total momentum in the x direction before they collide. So then we can write, Well, we can write m1 v1x initial plus m2 v2x initial equals m1 v1x final plus m2 v2x final. But we can simplify. Okay, so we know that v1x initial is plus v sub I. v2x initial is minus v sub I. v sub I is just the speed. In other words, v1x initial is plus 10 meters per second. v2x initial is minus 10 meters per second. We also know that m1 is 2m2. Okay. So this will end up being, after we plug that in, we will have m1 minus m2 v initial, and then v1x, and then we also have v1x final equals v2x final equals, we'll just call that v final, okay? So this is m1 plus 2 v final. So then that's enough to solve for v final. You get v final, maybe I should call this x final. Well, anyway, whatever. V final is m1 minus 2 over m1 plus 2 times v initial. And we said that m1 is 2 times m2. So this is like C2m2 minus 2 divided by 2 plus v initial. So that's like 2 minus 1 is 1, and that's 2 plus 1 is 3. That's 1/3. So this is plus 1/3 v initial. So I guess that means plus 3.3 meters per second, about that. So you say, okay, you have a big moose, 2 units of mass, moving to the right at speed v. You have a little moose, 1 unit of mass, moving to the left at speed v. They collide, their antlers lock, now they slide together on the icy tundra. The total momentum afterward is the same as the total momentum before. So then you can work out that the speed at which the 2 moose system slides after their antlers lock, in this case for this ratio of masses, is 1/3 of this initial speed of each moose. So if the initial speed of each moose going toward each other was 10 meters per second, then the 2 moose system here slides to the right, which is the direction of the bigger moose, at 3.3 meters per second. I think you're going to solve a similar question where instead you are told the final speed, you have to figure out the ratio of the 2 masses. Anyway, I wanted to give you one more example of a quantitative problem. So that's an example of a quantitative problem you can solve with momentum. You see, most of these problems that you can solve at this stage before we study energy in Chapter 5, they usually involve things like sticking together and sliding together. Or they might involve somebody tells you, maybe you know both initial velocities and somebody tells you one of the 2 final velocities, and you have to solve for the one other unknown. Because notice that otherwise you have, in principle, you have 2 unknowns in the final state, and you only have 1 equation. So next week in Chapter 5, energy is going to give us a second equation. But for cases where the things stick together, there's only 1 unknown because the final velocity of the 2 objects is the same. Okay, so you can ponder that, and I will see you in class for worksheet number 4.